Hi, everybody. Welcome back to Dave's Math Channel. I'm your host, David Tear, and this is my second video on section 3.4 of the Math Lovers book, which is on Fibonacci numbers and the golden ratio. Yesterday, I introduced Fibonacci numbers. There's really a lot you can say about them. I just gave a very brief introduction, kind of define them. But like I mentioned, I think they have tons and tons of useful properties, and one of those useful properties actually has to do with a very important irrational number called the golden ratio. So let's get right into it. What's the golden ratio? Well, the golden ratio has a simple formula. It is an irrational number, but it's a quadratic irrational. As a matter of fact, it has a simple formula. The symbol that's usually used for it is the Greek letter phi, which is shown on the left. There's actually two different forms of the Greek letter phi. This is kind of the variation of phi. The standard phi looks like the empty set symbol, circle with a vertical line going through it. This one more looks like has a single stroke. But anyway, this is the one that's used for phi, the golden ratio. And the formula is it's equal to 1 plus the square root of 5 all divided by 2. And as a decimal, you can approximate it. Of course, since it's an irrational number, the decimal never repeats or terminates. But if you want to round it to 10 decimal places, you get approximately 1.61803, 39887. And anyway, so that's what it is. And you might wonder why we care about this number. Well, turns out there's a lot of reasons. I'm just scratching the surface today, but I'll just tell you one reason why it's useful, and its connection with Fibonacci numbers. Let's look at the ratio of two consecutive Fibonacci numbers. So, for instance, yesterday I talked about the Fibonacci sequence, which begins 1, 1, 2, 3, 5, 8, and so on. And these numbers grow pretty fast. And I have them listed up to the 25th Fibonacci number, which is 75,025, which is a pretty big number. But let's just look at the ratio of consecutive Fibonacci numbers. So that's what I'm calculating in this third column. These big decimals, the first column of big decimal numbers, and you'll notice something interesting about these ratios. First of all, they converge, and they converge pretty quickly. I mean, they can, and it turns out they converge on the golden ratio. That's why the golden ratio is important in its connection with Fibonacci numbers. It turns out that if you take the limit as n goes to infinity of fn over fn minus 1, that limit is equal to the golden ratio. You can actually prove that. I'm not proving it here. I'm just kind of demonstrating it mathematically. So in the third column, I showed what these ratios are. In the fourth column, I showed the difference between these ratios and the actual value of the golden ratio. And you can see by the time we get up to F25 over F24, this difference is already just two parts in 10 billion, I believe. So this is the 10th decimal places, which is the 10 billionths. So it's already better than 1 part in a billion, precise estimate of the golden ratio. And I think I should just say one more thing. I don't mention this right here, but even though these numbers are converging pretty quickly, it also turns out that there's a connection between continued fractions. Remember, I was talking about rational convergence, I think last week when I was talking about continued fractions. I'm just going to jump the gun a little bit here. It turns out that if you calculated the continued fraction representation of the golden ratio, you get a representation that's all ones. All the continued fraction coefficients are equal to 1. You get 1, semicolon, 1, comma, 1, comma, 1, comma, 1, so on. Or you can just write as 1, semicolon, 1 with a line above it. That turns out to be the continued fraction representation of the golden ratio. And these ratios of Fibonacci numbers, these are rational numbers, obviously. They also turn out to be the rational convergence of the golden ratio. And so, for instance, the first one, 1 over 1, that's just 1. That would be 1 with no semicolon. And then the second one is 2 over 1, which you can also write as 1 semicolon 1. It's 1 plus 1 over 1. And then if you keep going like this, and then the third one, 3 over 2, that's 3 halves, that's 1 semicolon 1 comma 1. And you keep going like this, and they all look like this. So the last one here, the last of these ratios I wrote down, F25 over F24, which is only different from the golden ratio by 2 parts in 10 billion. That one is just the continued fraction of that would be 1 semicolon 24 more ones. So a total of 25 ones. And, that's very close to the actual golden ratio. But one thing I want to say about this, even though these numbers converge pretty quickly, it turns out that in terms of continued fractions, this is the slowest, believe it or not, this is the slowest possible converging sequence of rational convergence of any irrational number. You can prove this. Every other irrational number, if you can commute it as continued fractions, you get some coefficients that are bigger than 1, obviously. The only one where they're all 1 is the golden ratio. And every time you get a continued fraction coefficient that's bigger than 1, the bigger the continued fraction coefficients, the smaller the ratio is between the last continued fraction, the last rational convergent, the difference between the last rational convergent and the actual number. That difference grows by a factor that's approximately equal to the next continued fraction coefficient. Since for the golden ratio, all the continued fraction coefficients are 1, that implies that this is the slowest possible converging continued fraction. But it does converge pretty damn fast. I mean, one thing you have to realize, this is an exponentially converging sequence. And exponential decay or exponential growth are very, very fast, no matter what the exponent is. So it still converges very fast, even though it's the slowest possible convergence you can get. And another thing people sometimes say is that the golden ratio is the irrational it's the most irrational number there is, meaning it's the hardest irrational number to approximate as a rational number. In the same way I've just said, I guess if you want to approximate any other rational number to 1 part or 2 parts in 10 billion, you wouldn't need so many rational convergence, and the last one would probably have a smaller denominator. So anyway, that concludes my video for today on the golden ratio. Thank you for watching. Long live math, and I'll see you guys next time. Bye.